intensity of competition. What? Okay. And it's based on a joint work with Stefan Lauermann. I actually prepared a somewhat more ambitious toy model than the one I'm going to present to you today, but last night I decided it will cause so much confusion that I reverted back to some simpler model that I've already had. So if we have time at the end, we'll go to this more complicated toy example, but for now, let's go with this plan. So in markets with adverse selection, the extent of competition itself may be influenced by private information and may have significant effect on outcomes. This may arise due to costly solicitation of trading partners by informed parties, costly entry decisions of partially informed agents, availability of outside options that are related to values in the market in question. So these are but 3 examples of scenarios where the extent of participation itself might depend on the private information. So for concreteness, I don't mean to sell you this model as a concrete model of some specific market, but just so that to fix idea that you have some story in mind. Think that there are entrepreneurs, each seeking finance for a single investment project. And there are investors who look to acquire such projects. And the project may differ in value, and the entrepreneur knows the value of own project. And each of the entrepreneurs contacts a number of prospective investors trying to interest them in the project. Investors do not know the value, but they observe signals of the project's value, and based on it make acquisition offers. And finally, each entrepreneur selects from among the price offer made to her, selects to which investor to sell their project. So this is a sort of story that I'm not going to analyze seriously, but a story that, a motivating story of the sort of market or markets that I have in mind when I perform this analysis. Now, the main insight of the analysis will be that if entrepreneurs a contact initiation behavior depends on the value of the project of which they are informed, and this, which might be, such dependency might be consequence of contact initiation cost, if it's costly to initiate this contact. It could have significant effect on market outcomes. Specifically, equilibrium price may end up being non-competitive in the sense that the price will be bounded away from expected values even in the presence of seemingly many competitors. And and that the price might end up aggregating information poorly. So projects of different values might get the same price. So the information will not be aggregated into the prices well. This is the main insight that I'm going to try to sell you. Now, why are these insights valuable? A disconnect between price and value might have efficiency consequences. In the very basic environment that I will be discussing, trade is always desirable, so price is just a transfer. But very plausible extensions like adding costs to other side of the market would introduce efficiency considerations. In such a case, discrepancies between price and value and failure of price to aggregate information could translate to real economic costs. So this is one issue. Another insight, this insight also provides another a possible idea, and this is that it proposes adverse selection for explaining the phenomenon of sticky prices. So macroeconomists concern or talk about sticky prices, and they came up with a variety of explanations: institutional rigidities, menu costs, efficiency wages. So this story here might end one other such story, one other such element that creates a price, that creates sticky prices in certain situations. So to understand the basic issue, we do not need a market model of the sort that I've just outlined with many agents on both sides. Some of the main points can already be addressed in an auction-like interaction of a single agent, the counterpart of the entrepreneur in the story I just gave you, and a number of bidders, the counterpart of the investors that this entrepreneur contacts. And why, although this will be a basic auction model, because of this market story that I gave you, I don't want to think about it as a contribution to auction theory. I mean, maybe it does have a little contribution to auction theory. But this is definitely not in the mechanism design spirit that many of us have come to think of auctions. This is a market model, and this, what I call here an auction is just a component of a market model that can be embedded in a larger model of a market with adverse selection. I just pick it out because it already, this scenario captures most of what I need. So here's the model. There's a single seller and potential bidders, two states of the world. L and H for low and high, prior being denoted by rho, and the bidders have common values in state W. They have the value VW. With the content is that VL is smaller than VH. The low value is smaller than the high value. This is the value for all bidders. The seller knows W. Seller informed about the value of this good. The bidders are not. The seller solicits randomly drawn bidders at a cost S per bidder. So this is the main. If you look for a new element in this model, this is the main new element, that the informed seller solicits the bidders at a cost. Each solicited bidder privately observes a signal X that distributed, drawn from a distribution G that depends on the state. Remember, W denotes the state. It's either L or H. The number of bidders that have been solicited is unobservable to the bidders themselves. So don't think of it as an auction that the auctioneer assembles all these bidders in a large room and they see who is present. But think about it something like the story that I told you about these are different entrepreneurs contacting a bank or contacting an investor, and they don't know how many other entrepreneurs are contacting the same investor. Now, solicited bidders submit, so they are being solicited by the seller, then they submit bids simultaneously. Highest bidder wins. Ties are broken randomly. Payoffs when P is the winning bid are as follows. For the winning bidder is the value minus the price. For other bidders, it's 0. For the seller is the revenue, the price the seller gets, minus the costs that the seller incurred in soliciting bidders. So again, if you look at some new element in the model, it's this solicitation and the cost of solicitation. The bidder signals have support on X lower bar, X upper bar, conditional on W, on the value, the IID, so they're conditionally IID. The distribution function is atomless and has a density that's strictly positive on XX. I'm not going to use this in the presentation now anyway. So the likelihood ratio is weakly increasing. That means most higher signals are most favorable, indicative of higher value, more indicative of higher value. So X upper bar is the most favorable signal for the value, and X lower bar is the least favorable. And we make this assumption about the likelihood ratio. Okay, and the likelihood ratios of all the other signals are in between these two extremes. And it's monotonically, it's weakly increasing. So everything is standard so far, except that the auctioneer solicits the bids and at a cost. A pure solicitation strategy, we denote it by NL and H. This is the number of bidders to be solicited when the value is L and when the value is H, respectively. And so this is the seller strategy. For the bidders, a strategy is a bidding strategy. You've been solicited, you see a signal X. how much to bid. So its beta is a function from this interval to the set of possible bids. So you can calculate the interim belief of a bidder who has been solicited and got a signal X, knowing that the solicitation strategy of the seller is bold N. Bold N is a vector, NL, NH. It's not a number. Bold N is the pair, NL, NH. So given a solicitation strategy and the fact that you have been solicited and got a signal X, this is the probability of H. This is just a standard. The only thing I'm showing you here that in an ordinary common value auction, you'll have the same formula, except you will not have this ratio of NH over NL. Because in an ordinary common value, if it were an ordinary common value auction, you'll have the same number of bidders for both the high value and the low value. This will be 1. So this is the standard belief in, and here the new element is that the likelihood ratio, that this solicitation likelihood ratio also enters the calculation. You see, I wrote that the word that the probability of H conditional on being solicited. Of course, the bidder will have a role to play only when they are solicited, so I will just omit the word solicited. Whenever a bidder makes a decision, clearly they have been solicited. So just to repeat, the effective likelihood ratio in this problem is consists of 3 likelihood ratios, a product of 3. Likelihood ratio from the prior, from the signal, and from solicitation. And again, this little ratio there, NH over NL, is what distinguishes it from ordinary auction analysis. So a bidding equilibrium given bold N, so let's freeze the behavior of the seller, take it as exogenous for a second, and speak about just the behavior of the bidder. So bidding equilibrium given a certain behavior of the seller is a bidding strategy such that for all X, the bid prescribes by beta maximizes the bidder's payoff given the solicitation N and given that other bidders use the same bidding strategy beta, not submit the same bids, but the same bidding strategy. The equilibrium of a standard common value auction is a special case with NH equal to NL. Okay, so now I want to show you an example to show you why there might be something interesting here. So here's the example. Let's assume the two values are 0 and 1 with a uniform prior. They occur with probability 1/2, and the range of signals is 0, 1. And the density functions are as shown, the G in state H, it's this nice increasing function, 0.8 plus 0.4 times x. In state L, it's a nice decreasing function, 1.2 minus 0.4x. So the monotone likelihood ratio is satisfied because the hg is increasing, the little g is increasing, for L it's decreasing. So of course the likelihood ratio is monotone, it's needed. Now, suppose that there are in total n prospective bidders, and that this is what the auctioneer does. The auctioneer in state L solicits 6, in state H solicits 2. I'm not saying it's good for the auctioneer. I'm just saying suppose, take this as given. So the claim is that select any bid, B upper bar, in this interval 1/3 to 0.4. There's a bidding equilibrium in which everybody bids B upper bar, regardless of the signal. Those of you who thought or worked a little bit about auctions should surprise you a little bit, because we don't expect it to happen in such an auction. Or let's say in a common value auction, we don't expect it to happen, and here it happened. Yes? Yes. The N is exogenous for now. We'll get to it. Of course, the N will have, if we want a full equilibrium, it will have to be determined optimally by the seller. And here it's clearly not optimal. It's clearly not optimal. But I'm saying take it as given. and look at the equilibrium. So you have this atom. Everybody is bidding the same. I want to explain to you why we have this atom. So just like a couple of more pieces of notations, pi will be the probability of winning with bid B at value W, given that everybody uses the strategy beta and that the auctioneer solicits NW bidders in this situation. So this is just a symbol. So I'm just going to use, this is the probability of win conditional on, in a state conditional on the behavior of the seller and the other bidders. And then we can calculate, given this pi, this piece of notation, we can calculate the posterior probability of a bidder of the value H, bidder who has been solicited, observe the signal X, and wins with bid B, given that the behavior of the others is given by this strategy. So we do the same calculation as before, except we have here the ratio that's coming from the winning probability in the two states. So this is standard. And this is increasing in X, this ratio is increasing in X, so this probability is increasing in X by the monotone likelihood ratio, because this is increasing in X. Therefore, this whole thing is increasing in X. So now I want to convince you that this is an equilibrium. So first of all, see what happens. What's the expected value conditional on winning at B? So a bidder who wants to follow the equilibrium strategy, what's the expected value conditional on them winning? So the 0 is coming from that the first component is the probability that the true state is L times the value at state L, which is 0. This is where the 0 is coming from, plus the probability that it is state H, conditional on this information, on winning and seeing the signal X, times the value at state H. This is greater or equal than this same probability if we substitute, instead of X, we substitute the lowest signal. Because I told you this probability of H is monotone in X, this conditional probability. So we have this greater or equal, and now I substituted the numbers for you in this calculation. Remember on the previous page I gave you the formula of this probability, conditional probability. I gave you this formula, and now I substitute the data from the example into this formula. This is what I'm doing here. And I'm getting, I've already made the calculation for you, it's 0.4. See, 1 is VH. And this rest of the calculation is from the formula. And remember, this B upper bar was chosen to be below 0.4. So that means for a bidder who bids at the atom, conditional on winning, they are fine. They are not losing. The expected value is greater or equal than what they are paying. Now, question is, the main question about this being in equilibrium is, why wouldn't they overbid a little bit and win for sure? This is, you might think, the temptation. So let's see what happens to a bidder who overbids. So expected value conditional on winning at a higher bid, B prime. Here I calculate it. Again, I omitted the case of, because VL is equal 0, it's just the probability of H times VH. Now notice that here the inequality, okay, so I did two things in the transition here. First of all, I omitted the conditioning on winning at B prime. Why? Because if you bid B prime, you win for sure. Everybody is bidding B upper bar, and you bid above them. So if you bid B prime, you win for sure. There is no question of conditioning on winning. You win for sure. So I omitted this. And I changed, and here, this transition is I went from arbitrary signal X to the highest signal. And because this probability is increasing in X, I get this inequality. And again, I substituted in that formula the numbers for you, and I get that they are equal to 1/3. The formula that I'm talking about again is, is this formula. I substituted the numbers in it. I know all the numbers. So from the example. So I get 1/3. And by construction, B upper bar was greater or equal than 1/3. And I'm talking about overbidding. So this B prime is above B upper bar. So that means if you overbid, the expected value that you are getting is 1/3, and it is smaller than you bid. You are winning for sure, and you are getting negative payoff. So nobody wants to overbid. Now, there is one more thing to check. And does anybody wants to undercut, to bid underneath the atom? Of course not, because then they lose for sure and get payoff of 0. We said that the atom, they get non-negative payoff. They don't want to overbid. They don't want to bid below. So this is an equilibrium. Yeah, somebody raised their hand. Now, what are the ingredients here? And I emphasize to you, at least I view it as a somewhat interesting point, that you have this this competitive bidding situation, and you have an atom, and nobody, even the person with the highest signal, bids at the atom, and they don't want to overbid it and win for sure. So how did this atom come about? Well, it required two things. The ingredient answer, bidding at the atom is profitable for everybody, even for the person with the lowest signal, and that overbidding it is unprofitable, even for the person with the highest signal. So what's a sufficient condition for it? Sufficient condition is that this equilibrium bid lies between these two expected values. It's larger than the expected value of winning for sure with the highest signal. This is the expected value of winning for sure with the highest signal. And it's and this side says that you don't want to overbid this bid. And it is smaller than the expected value for a lowest type of winning in B, which means it's profitable for everybody to bid at the atom. Nobody is losing by bidding at the atom. Now, this is achieved by two elements in the assumptions that I make in the example. Element one is that this ratio is 3. Bidding at the atom ensure against the bad state. In the bad state, they don't want to win because the value is 0. They don't want to pay positive price for something that's worth 0. But there are more bidders in the state L than in state H. If they're all bidding the atom, if you also bid in the atom, you get a little insurance because there are more people bidding in state L in the atom, so your probability of winning is lower. And there are fewer people in the state H, your probability of winning is higher. So staying at the atom insures you. In this case, it gives you, this ratio is 3. Probability of state H conditional on winning at B is 3 times larger than probability of state L. So this is one thing. The other thing is the solicitation curse. This ratio is small. Even if you have the highest signal, the mere fact that you have been solicited already makes you pessimistic and don't want you and make you reluctant to overbid and win with probability 1, because this solicitation cost, this ratio is coming from the signal, and this means even if you have the high signal, the odds of being solicited in state H are smaller than the odds of being solicited in state L. So you are pessimistic. By mere fact of being solicited, you are pessimistic, and you don't want to overbid and win. Okay, these are the elements. Now, additional observations. These arguments that I gave you hold. I used NH equals 6 and L equals 2. Of course, I didn't use the absolute numbers. I used only the ratio. So, of course, if I used any numbers, 3,000 and 1,000, 6,000 and 2,000, it will be the same equilibrium construction. I didn't use the absolute numbers at all. And, of course, there's nothing special about 1/3. I could choose other sufficiently small ratios, I don't know, 1/4 or something, and would give rise to a similar construction. And it follows from subsequent results that I'm not going to discuss here today, that if this is the case, again, it's nothing special about 3, but for example, if NL is equal to, if this ratio holds and the numbers are sufficiently large, then there is no equilibrium without atom. So this is not something that I constructed, some knife edge thing that I constructed. It's if these ratios are like so and the numbers are large, they will simply not be an equilibrium that doesn't have an atom. So it will be unavoidable. But this is something. Now, in contrast, if this holds, and notice this includes the case of the ordinary common value auction in which NH is simply equal to NL, then there's essentially no atom. I say essentially because if NH is exactly equal to NL, you can have some sort of insignificant atom at the bottom. It's not worth our time to talk about it. Think about it that an atom of the sort that I described here doesn't happen if NH is greater or equal than NL. Any questions? So what are the insights for information aggregation? The price is, in this example, is beta hat in beta upper bar in both states. It's smaller than the expected value, so the auction does not become competitive. Even if I made these numbers, NH and NL, very large, the auction does not become competitive. The price, I can keep it bounded away from below the ex-ante expected value. And there's no information aggregation. A trade always takes place at the same price. So the prices reflect no information. So, so now we are going to the question that Bhaskar raised a few minutes ago. The example that I've just shown you, it is just a bidding equilibrium. It's not a full equilibrium. Of course, in this example, the seller solicitation, it's costly for the seller to solicit bidders. It's not optimal because if all bidders bid the same bid, you want to solicit only one bidder in each state. Why spend money on more bidders if they are all going to bid the same bid? So of course, this 6 and 2 is non-optimal from the point of view of the seller. But the question is, so one immediate question is whether such an atom, like we saw in the example, with its consequences for the competitive of the prices and the information aggregation of its failure, can arise in a full equilibrium in which the auctioneer solicits bidders optimally. So I want to show you by another example that this is possible. So let me first of all tell you what the full game is. Call it the full game, call it gamma of S. This is the game that consists not just the bidding, but also the solicitation. Assume, and I put it as a function of the solicitation cost. Parameterized by the solicitation cost, the assumption is that there are, in the game gamma S, there are NS bidders, and that this number exceeds VH over S. And this implies, this assumption implies that the seller never wants to solicit all the potential bidders. It's never optimal to solicit all the potential bidders. And this makes the calculation simpler. A symmetric and pure strategy equilibrium of gamma consists of a bidding strategy beta and the solicitation strategy bold N, such that beta is a bidding equilibrium given NL and H. I've already defined to you what a bidding equilibrium was. And the solicitation is optimal. Solicitation being optimal, meaning the number of bidders solicited in state W indeed maximizes the expected winning bid of the seller minus the cost of solicitation. By the way, to talk about